Welcome to today's deep dive. And I have to warn you right up front, we are starting with a number that is just staggering.
It really is. It's one of those stats you have to read twice.
Right. So here we are in 2026, and the global cloud computing market is officially projected to cross $1 trillion in annual revenue this year. Which, I mean, that's massive on its own.
Oh, absolutely. It's the foundation of the whole digital economy now.
Exactly. But hiding inside that trillion-dollar pie is this other number that just stopped me in my tracks.
Yeah.
Out of all that money, companies this year will waste $27.1 billion on cloud assets that are completely 100% idle.
Yeah, and we really need to emphasize that word idle.
Not underused, right?
Right, not running inefficiently, just doing absolutely nothing but spinning the meter. It is a financial hemorrhage of, honestly, historic proportions.
And it's just operating entirely in the shadows.
Exactly. I mean, to put that $27.1 billion into perspective, we are talking about a waste margin larger than the GDP of several small nations. And it's entirely dedicated to, blinking lights in data centers that no one is utilizing.
Wow. Just sitting there.
Just sitting there. And the reality we have to confront today is that the vast majority of this waste isn't even happening in some hyper-complex, heavily trafficked production environment.
Which is what you'd assume, right?
Yeah, you'd think it's the big stuff, but no, it's quietly accumulating in the background of just everyday software development.
Which brings us perfectly to our mission for this deep dive, because we aren't just here to gawk at big numbers or throw our hands up at the scale of the cloud.
Right, that doesn't help anyone.
Right. The goal today is to dissect exactly why this waste is embedded into modern infrastructure. And more importantly, we're going to unpack the actionable, highly technical strategies that organizations are deploying in 2026 to actually stop the bleeding.
And we have an incredibly robust stack of sources driving this analysis today.
I really do.
We're looking at the operational design philosophies of Prasad Bond, who's an engineering writer. He examines cloud infrastructure through this really pragmatic lens of mechanical engineering and manufacturing.
Which is such a cool way to look at it.
It really is.
Yeah.
And we're pairing that with granular 2026 enterprise cloud waste data from Vendor Benchmark, which actually recently rebranded as Vera AI.
Right, Vera AI.
Yeah, and they pulled telemetry from over 700 enterprise cloud environments for this.
So it's a massive data set.
Huge. And to figure out the actual technical fixes, we're pulling remediation strategies from modern optimization platforms like usage.ai and cast.ai.
What I really appreciate about this specific stack of research is the whole overarching premise. Basically, cloud waste is not a moral failing.
Exactly.
It's not about pointing fingers at engineers or saying people are lazy. It's a structural engineering flaw.
That is the critical framing for this whole discussion. If you're an engineering leader or, a founder listening to this, your first instinct is often to assume your teams are just being careless.
Sure, why didn't you turn the lights off before you left the room?
Right, exactly. But when you look at the data, you realize it's not about human laziness at all. It's about systems missing fundamental operational boundaries.
So I want to start right there with that philosophical root cause. Because Prasad Bande introduces a concept that just completely shifted how I view cloud computing architecture.
The paradigm blind spot.
Yes. He argues that the entire tech industry dragged this legacy assumption, like a ghost of the old data center days, into a brand new economic model.
Yeah, for decades, the entire IT industry operated within a very specific data center mentality.
The on-premise world.
Exactly. In an on-premise world, a physical server sitting in a rack is owned machinery. The capital expenditure, the massive upfront cost to buy the hardware, that's already happened.
They've already spent the money.
Right, the server physically exists.
Yeah.
Therefore, the default operating assumption that we cultivated over 30 years was basically servers must always be available unless someone actively has a reason to turn them off.
Because availability was the ultimate metric of responsibility, right?
Yes. I mean, if you spent $50,000 on a server rack and it's sitting in a colocation facility down the hall, you don't unplug it at night to save electricity.
Right, the fixed cost is sunk. The machine is yours.
Exactly. But then the industry migrated to the cloud and they brought that exact same behavioral conditioning with them.
But the cloud isn't owned machinery.
No, it's not. The cloud, as Bond so brilliantly frames it, is a running meter.
A running meter, I love that.
It is a purely variable cost model. Every single CPU cycle, every gigabyte of RAM, every second a resource is powered on, a microscopic financial transaction occurs.
And yet we kept the old habits.
Yeah, the inherited behavior, that assumption that infrastructure should just remain on by default, it was just copy-pasted into this pay-per-use economic reality.
Okay, I see the historical through line there, but I have to push back a little on the idea that this is just some innocent paradigm hangover. I mean, we are in 2026. The cloud has been mainstream for over a decade. Are we really saying that platform teams and senior developers simply don't realize they're leaving the meter running?
It's a good question.
It just feels like there has to be a conscious choice being made somewhere to just ignore the cost. Are they just being careless?
It's a really fair challenge, but when you look at the incentive structures within an engineering pod, the picture becomes clear. Developers are optimizing for the metrics they're actually measured against.
Which are what, usually?
They're measured on deployment velocity, feature delivery, and system uptime. They are almost never measured on infrastructure unit economics.
Okay, that makes sense.
The system is simply missing a basic structural operating question at the exact moment of creation, which is, when is this specific environment actually allowed to run?
That question just isn't part of the provisioning template.
It rarely is. Because of that legacy data center mindset, uptime is just assumed as a baseline rather than justified as a requirement.
Right.
Provisioning decisions are made in silos by individual teams, and the actual resource schedules are almost never tethered to the physical working patterns of the humans using them.
There's a scenario in the Bond research that really illustrates the physical absurdity of this. Let's say a development team spins up a Kubernetes cluster specifically for staging and testing a new feature.
A very common scenario.
Right. And the team works a standard schedule, let's call it 40 hours a week. They push their last commit, shut their laptops, and go home at 7 p.m. on a Friday.
Yep.
But the AWS, or Azure billing meter, it doesn't know it's Friday night. It doesn't recognize the concept of a weekend.
The hypervisor just keeps allocating the compute.
It just keeps running for 168 hours a week, even though the developers are only interacting with it for 40 of those hours.
The math on that is brutal.
It really is. Mathematically, for 128 hours a week, which is roughly 76% of the total time, that non-production environment is burning cash while literally zero human or automated testing is happening.
And, that scenario only accounts for time-based waste.
Right, there's more.
Oh, yeah. If we layer on the psychology of over-provisioning, which usage.ai explores in depth, the waste just multiplies. Engineering teams consistently size their infrastructure for peak theoretical demand.
Because they're scared it might crash.
Exactly. Or, more commonly, they over-provision simply because they are uncertain about how a new microservice will behave in the wild underload.
So they basically buy an insurance policy using company money.
That's a perfect way to put it.
They allocate these massive virtual machines because they're terrified of a CPU bottleneck taking down their application.
That is the core psychological driver right there. They prioritize performance headroom or, a safety buffer over cost efficiency.
Nobody wants to be the guy who broke production to save $50.
Right. The ultimate nightmare for a site reliability engineer is an outage caused by resource exhaustion. To neutralize that personal professional risk, they just pad the resource requests.
So when you combine those two factors, the inherited, always on default from the data center era, plus the active risk avoidance of over-allocating capacity, you don't have a system designed for efficiency.
Not at all.
You have a system designed for maximum spend. And when you scale that behavior across hundreds of discrete engineering teams inside an enterprise, that is how you arrive at that staggering $27.1 billion figure.
Which brings us to the forensic breakdown. Now that we understand the behavioral and structural why behind the running meter, we have to look at what this actually manifests as on a monthly invoice.
Right. Let's look at the actual bills.
The Vera AI benchmark analyzed over 700 enterprise cloud environments, and the aggregate data reveals that the average organization is wasting between 28 to 34% of its total cloud spend.
Let's contextualize that for you listening right now. If your organization has an annual cloud budget of $10 million, which is fairly standard for a mid-market tech company today, you are essentially taking $3 million, putting it in a pile, and setting it on fire every single year.
$3 million that could have been allocated to engineering headcount, research and development, or just extending runway.
And Vera AI categorizes that specific waste into 4 primary buckets, right?
Yes. Let's look at the largest offender first, which accounts for 38% of the total waste footprint. They call it idle and zombie resources.
I love that term, zombie resources. But how are we defining a zombie in a cloud context?
So these are infrastructure components that are technically running, passing health checks, and incurring hourly costs, but they are generating absolutely zero business value.
Give me some examples of that.
The most common examples are stopped EC2 instances in AWS that are still holding on to attached Elastic Block Store or EBS volumes.
So the compute is paused, but the storage disk is still costing you money.
Exactly. We also see thousands of unattached load balancers, idle relational database instances with zero active connections over a 30-day period, and orphaned backup snapshots from environments that were deleted months ago.
Here's where it gets really interesting for me. It's essentially like paying premium downtown office rent for an apartment you moved out of 3 years ago simply because you forgot to hand the physical keys back to the landlord.
That's spot on.
The landlord, in this case the cloud provider, doesn't care if the desks are empty. The lease is active.
That physical analogy translates perfectly to the API reality. Vera AI notes that zombie resources are actually the fastest growing category of waste right now.
Why is it growing so fast?
The mechanical reason for this is a lack of automated decommissioning workflows. Let's say an automated CI/CD pipeline spins up a virtual machine, attaches a 500 gigabyte storage disk, and runs a test.
Okay.
When the test is done, the script might issue a command to terminate the compute instance. But if that script wasn't explicitly written to also delete the underlying block storage and release the static IP address, those orphan components remain.
They just hang around forever.
They just sit there in the provider's console, practically invisible to the naked eye, accruing charges month after month.
Okay, so that silent accumulation of zombies is 38%. Category 2 accounts for 34% of the waste, which is over-provisioned compute and memory.
Right.
And this ties directly back to that psychological fear of outages we discussed, sizing for the absolute worst-case scenario.
The telemetry data here is genuinely surprising, even for me. When Vera AI measured the actual utilization of production compute across these 700 enterprises, the median CPU utilization hovered around 22%.
Wait, I need to make sure I'm interpreting that correctly. Are you saying that in live production environments, nearly 80% of the processing power companies are paying for is just sitting idle?
Yes. 78% of the compute capacity that organizations have formally procured and are being billed for by the second is essentially dead headroom.
That is wild. That's the equivalent of buying a fleet of long-haul semi-trucks just to deliver a single pizza every day, on the off chance you might one day need to move a house.
It really is. And the issue, as usage.ai points out, is the compounding financial nature of this specific inefficiency.
Because it's an ongoing cost.
Exactly. This isn't a one-time capital mistake. It is continuous, recurring operational expense waste.
So if you provision an instance that costs $2 an hour and it runs at 20% utilization, you don't get a discount.
No discount at all. You still pay the full $2. As microservice architectures grow and these over-provisioned templates are replicated across multiple geographic regions, the financial inefficiency multiplies exponentially.
Which naturally leads us to category 3, which I find incredibly ironic. Unused licenses and commitments make up 18% of the total waste.
Yeah, it's a painful one.
I say this is ironic because these commitments are specifically purchased to save money in the first place.
Exactly. This category stems entirely from well-intentioned procurement strategies. Cloud providers offer instruments like reserved instances or savings plans.
Right, the bulk buy discount.
The basic proposition is if you commit to a baseline level of compute usage for a 1-year or 3-year term, we will give you a steep discount, sometimes up to 40 or 50% off the on-demand price.
The classic volume discount. The provider gets revenue certainty, and the customer gets a cheaper unit rate.
In theory, yes. But in practice, organizations struggle immensely to forecast their infrastructure needs over a multi-year horizon.
Because things change so fast in tech.
Exactly. So they overcommit. The Vera AI data reveals a brutal mathematical reality about these instruments. The break-even point for a standard AWS reserved instance requires that instance to be actively utilized roughly 71% of the time over the life of the contract.
Oh, wow, 71% just to break even.
Yes. If your utilization drops below that threshold, the money you spend paying for the unused portion of the commitment actively eclipses the discount you received.
So if a team refactors an application 6 months into a 1-year commitment, and they suddenly need 30% less compute, they are actually losing money because they're locked into paying for that baseline.
Precisely.
It's like buying a non-refundable prepaid yearly gym membership in January to get a 20% discount, but you stopped going in April. You would have been vastly better off just paying the higher daily drop-in rate.
That's exactly how it works. And the data shows the median organization runs their commitments at about 74% utilization.
So they're barely scraping by.
They are agonizingly close to the break-even line, essentially wasting a massive portion of the discount they fought so hard to negotiate.
Which brings us to category 4.
Right. Finally, that brings us to category 4, data transfer and egress inefficiency, which constitutes the final 10% of the waste.
Now, egress is a topic that always feels a bit like a hidden tax to me. Why does it actually cost money for data to move around, especially when it's moving between data centers owned by the exact same cloud provider?
There is a physical reality and a strategic reality to egress.
Okay, let's hear the physical one first.
Physically, the cloud providers are laying and maintaining incredibly expensive, high-bandwidth fiber optic trunks under oceans and between cities to connect their availability zones and regions. There is a real, tangible cost to maintaining that network infrastructure.
That makes sense. But strategically?
Strategically, egress fees function as an economic moat. Providers do not charge you to bring data into their ecosystem.
Of course not.
Right. But they charge you to move it out or to move it across boundaries because they want to disincentivize you from using competing services.
Hotel minibar economics.
Yeah.
Free to look, very expensive to touch.
I love that. And teams routinely overlook this because the unit cost per gigabyte seems microscopic, like fractions of a cent.
It's just a tiny line item.
But let's say a developer builds a microservice in Availability Zone A, and it constantly queries a database in Availability Zone B because they didn't account for latency boundaries in their architecture.
Oh, I see where this is going.
Yeah, every single one of those millions of packets incurs a tiny fee. For data-intensive applications, egress waste can suddenly balloon to represent 20 to 40% of the entire cloud bill.
Just from poor architecture.
It is almost always driven by fundamental architectural decisions made very early in the development lifecycle.
Okay, so we have the 4 pillars: zombies, over-provisioning, unused commitments, and egress. But the Vera AI benchmark gets much more granular than just these categories, doesn't it?
It does. They actually mapped where this waste is most prevalent across different demographics of the tech landscape.
Let's look at the cloud providers themselves. Do AWS, Azure, and Google Cloud customers all waste money at the same rate?
They do not. The telemetry shows that Microsoft Azure environments consistently exhibit higher waste rates, averaging 33%,
Now the other.
compared to AWS at 29% and Google Cloud Platform at 27%.
I'm really curious about the mechanics behind that discrepancy. Are Azure customers inherently worse at managing infrastructure, or is there something structural about how Azure is built?
It is deeply structural, tied to the architectural design of the platforms themselves. Azure utilizes a highly complex resource hierarchy. You have management groups, subscriptions, resource groups, and then the individual resources themselves. This multi-layered structure is incredibly powerful for enterprise access control, but it creates profound dark corners for orphan resources to hide.
Because it's just too deeply nested.
Exactly. If a platform engineer in AWS deletes a CloudFormation stack, it generally takes everything associated with it down.
That's all bundles.
Right. But in Azure, if an engineer deletes a virtual machine but forgets to delete the overarching resource group or the detached virtual network interfaces inside it, those components persist.
They just become zombies.
And the data also suggests that, historically, Azure's native cost management dashboards lag slightly behind AWS Cost Explorer in actively surfacing these highly specific decoupled zombie resources.
So provider complexity breeds waste. I have to imagine that organizations trying to run multi-cloud architectures, juggling AWS, Azure, and GCP simultaneously, are facing an absolute nightmare.
The data absolutely confirms that instinct. Multi-cloud environments generate the highest aggregate waste rates, sitting at 34%.
Not surprising.
When you operate across multiple providers, you're dealing with redundant native tooling, overlapping third-party licensing, and the immense friction of trying to enforce a consistent tagging and governance taxonomy across entirely distinct provider APIs. It just diffuses visibility completely.
The provider breakdown is fascinating, but the industry breakdown in this report completely defied my expectations. When Vera AI sliced the data by vertical, the worst offender was government and the public sector, carrying a massive 41% waste rate.
Yeah, that's a huge number. But the primary driver there is entirely divorced from engineering capability.
What is it then?
It is a structural byproduct of public sector budget cycle dynamics. Government procurement typically operates on a strict use-it-or-lose-it annual basis.
Right, the classic bureaucratic trap. If an agency doesn't spend its entire allocated budget by the end of the fiscal year, the finance department assumes they didn't need it, and their budget gets slashed for the following year.
Which creates a deeply perverse incentive structure. IT procurement teams in the public sector are heavily motivated to commit to maximum cloud capacity, buying massive blocks of reserved instances right before the fiscal year closes, simply to secure the funding.
So they buy just to spend the money.
Yes. But once that capacity is purchased, there is absolutely zero corresponding financial incentive for the engineering teams to optimize the utilization of those resources during the actual year.
That explains the government sector. But here's the data point I really want to unpack. Vera AI shows that cutting-edge technology companies, the ones building the actual software we use, waste 29% of their spend.
Yes, they do.
That is significantly worse than heavily regulated financial services and healthcare companies, which sit at around 24%. So what does this all mean for tech companies? Why are the most cloud-native organizations wasting more money than the legacy banks?
It is a brilliant paradox, and it highlights how engineering culture dictates infrastructure reality. Technology companies, especially high-growth SaaS or consumer tech, prize engineering velocity and developer autonomy above almost every other metric.
They want to move fast and break things.
Exactly. Their competitive advantage relies on developers being able to build fast, experiment freely, and deploy to production multiple times a day.
So they intentionally strip away red tape. They want frictionless infrastructure.
Yes. But that rapid iteration culture frequently overrides or intentionally ignores FinOps guardrails. If a developer wants to spin up a massive cluster to test a machine learning model, tech companies want them to be able to do that instantly without waiting 2 weeks for a finance committee approval.
Freedom creates sprawl.
Conversely, financial services and healthcare operate under massive compliance and regulatory mandates, frameworks like PCI DSS or IPEA.
Right, a lot of rules.
This regulatory burden absolutely increases their baseline operational costs, but it also mandates incredibly strict governance frameworks. A developer at a Tier 1 bank generally cannot just spin up a shadow cluster without going through automated security checks, mandatory tagging policies, and architectural review boards.
So the red tape actually stops the waste.
That compliance-mandated governance inadvertently forces a level of cost hygiene that tech companies simply opt out of.
Regulation creates boundaries, and boundaries accidentally save money. But if we drill down past the industry verticals and the cloud providers and look strictly at the workloads themselves, the Vera AI data points to one specific area as the absolute worst offender.
Development and test environments.
Dev and test workloads carry an astonishing 61% waste rate across the board.
They generate 2.4 times the waste of production environments.
61% waste on non-production. This brings us full circle to Prasad Bond's core thesis. They are the worst offenders because they are the exact environment suffering from the 168-hour-a-week running meter while only being used by humans for 40 hours.
Exactly. And because this specific workload profile is universally the single largest culprit of pure idle waste, it is exactly where organizations must begin their technical remediation.
You have to start where the bleeding is worst.
Right. You don't start by trying to squeeze 2% more efficiency out of a highly tuned production database. You start by turning off the development servers on Sunday night.
Which transitions us perfectly to the first technical strategy we need to dissect. Let's get into the solutions. If dev and test environments are bleeding 61% of their spend, how do modern organizations stop it in 2026?
Well, Prasad Bond outlined a strategy he calls the Non-Production Runtime Charter, or the one-week zero-cost process shift.
The claim here is pretty bold.
It is. The claim is that an organization can recover 4 to 8% of its total cloud spend in a matter of days, with extremely low engineering effort, and crucially, without buying a single new piece of software.
That sounds almost too good to be true. How does that work?
The elegance of this strategy lies in its reliance on existing native cloud controls combined with a forceful shift in organizational communication. Implementing this requires navigating a specific operational sequence.
Walk us through how a FinOps team actually deploys this charter in reality. Because I have to imagine there is significant cultural friction from engineers who don't want their toys turned off.
Oh, the friction is absolutely the hardest part. The deployment begins by defining rigid, organization-wide allowed runtime windows.
Okay, setting the hours.
Right. Leadership must establish a default schedule for all development, testing, and staging environments. For instance, declaring that non-production environments are only authorized to run from 08.00 to 20.00 local time, Monday through Friday.
So you are explicitly redefining the default state of the infrastructure from always on to business hours only.
And you couple that with a blanket mandate. Any requirement for a 247 non-production runtime is no longer a given. It is now classified as an architectural exception that requires explicit, documented justification from an engineering director.
Okay, establishing the rule on paper is one thing, but practically, how do you enforce it? You can't just flip a master switch and hope you don't take down a production dependency.
This is where the technical prerequisite comes in. You must leverage your existing tagging taxonomy.
Which means?
A FinOps team cannot enforce a schedule if they don't know which resources belong to which environment. They use native cloud APIs to scan for metadata tags like environment equals dev or environment equals staging.
Gotcha.
This allows them to produce a definitive inventory of all non-production resources using the standard billing consoles provided by AWS, Azure, or GCP.
Assuming they have those tags in place, how are they mechanically automating the shutdown? Are developers expected to log in and click stop before they go home?
Absolutely not. Relying on human memory to turn off cloud infrastructure is a guaranteed failure.
Yeah, that would never work.
You implement basic scheduling using native automation. AWS, for example, offers the AWS Instance Scheduler. It's a relatively simple serverless solution that uses Lambda functions and DynamoDB to automatically start and stop EC2 and RDS instances based on a defined schedule.
Or they could just build it into their deployment pipelines, right?
Exactly. Teams can embed simple cron jobs into their existing CI/CD pipelines. The technical execution is actually trivial.
The technical part is easy, but the cultural part seems volatile. I can hear the engineering complaints now, like I logged in on Saturday morning to fix a bug and my dev server was gone, so I lost 3 hours of productivity.
That is the exact friction leadership has to absorb during step 4, which is communicating and enforcing the hard rule. You have to update your infrastructure as code templates, your Terraform modules or CloudFormation scripts, so that every single new environment requires a runtime schedule parameter to even compile.
Wow, force it at the code level.
And when engineers push back, Bond suggests using a very grounded physical analogy to reframe their perspective.
Oh, this is my favorite part of his writing. If you run a machine shop, you don't leave every motor spinning overnight just because someone might need a drill press tomorrow.
Exactly.
Such a great visual. If you run a manufacturing floor, you would never allow your foreman to leave every single high-voltage drill press, lathe, and conveyor belt running at maximum RPMs overnight and through the weekend, simply because a machinist might want to come in on Sunday morning.
It would be insane.
It would burn out the motors, create a massive fire hazard, and the electricity bill would bankrupt the company. You turn the machines off when the shift ends. So why do we treat cloud compute differently?
The answer is lack of sensory feedback. If you walk onto a factory floor, you can hear a drill press running. You can feel the heat. You can't hear a virtual CPU spinning in a data center in Virginia.
That is such a good point.
Bond emphasizes that enforcing this runtime charter isn't about micromanaging developers. It is about restoring operational dignity and runtime hygiene to the engineering culture.
He has a phenomenal quote that captures this perfectly. He writes, "Always-on non-production is often not agility. It is an unattended meter with a very good UI."
It completely shatters the illusion. Engineering teams often operate under the false assumption that leaving everything running makes them agile. In reality, they have just left the taximeter running on the curb while they went inside a restaurant to eat dinner.
And what's the actual savings from doing this?
By implementing this basic scheduling charter, the Vera AI benchmark notes that an organization can realistically recover up to 8% of total spend in less than a month, requiring perhaps 20 to 40 hours of initial engineering effort to set up the automation.
An 8% recovery on a multi-million-dollar bill for 40 hours of work is an unmatched ROI. But as we touched on a moment ago, a runtime charter is entirely dependent on being able to identify what a resource actually is.
Right, you need to know what you're turning off.
You can't safely target a server for a weekend shutdown if you don't know who owns it or what it does. This brings us to the second, much deeper technical strategy, which is FinOps governance and tagging compliance.
Because while simple scripts work for basic dev servers, modern infrastructure eventually scales beyond what human ad hoc processes can manage. Vera AI analyzed the top 25% of performers in their dataset.
The ones who are actually doing this well.
Yes, the best-in-class enterprises that miraculously maintain waste rates down around 18%. And what separates these elite organizations is not initially some magical AI platform. It is ruthless, systematic governance, and near-perfect tagging compliance.
Let's talk about the metadata crisis, because tagging is where the money literally disappears into the void. The benchmark found that the median enterprise operates with only 68% resource tagging compliance.
Let's walk through the mathematical implication of that statistic. Nearly 1/3 of all cloud resources running in a standard enterprise environment carry absolutely no attribution metadata.
They have no digital name tag, no owner, no project code, no cost center assigned.
Precisely. If you are managing a $10 million cloud budget, that means approximately $3 million of that spend is a complete black box.
Wow.
The central IT or FinOps team has no idea who provisioned it, what application it supports, or if it is still needed. And crucially, no FinOps practitioner is ever going to aggressively shut down a $3 million mystery workload because there is a non-zero chance they might accidentally sever a critical, undocumented dependency for a production application.
So the fear of breaking something forces them to just keep paying the bill. So how do the top 25% of organizations solve this? Do they just yell at developers more effectively?
No, they remove human choice from the equation entirely. They enforce tagging at the moment of provisioning using strict API gateways.
How does that look in practice?
In AWS, this is typically done using service control policies, or SCPs.
Yeah.
In Azure, they use Azure Policy. These are organizational level rules that intercept infrastructure requests.
So it stops it before it starts.
Exactly. If a developer runs a Terraform script to spin up a new database, and that script does not contain required tags like owner, cost center, and environment, the cloud provider's API outright rejects the deployment request. It throws an error. It simply will not launch.
If it's not tagged, it doesn't launch. It becomes a hard deployment blocker.
Yeah.
But how do you actually make engineers care about the cost? Because an engineer's primary job is to build features and ensure uptime. They aren't accountants.
This brings us to what is widely considered the most powerful organizational strategy in cloud financial management: the transition from centralized IT billing to strict showback and chargeback models.
I hear these two terms used interchangeably all the time. What is the functional difference between showback and chargeback?
Showback is purely about visibility and psychological awareness. It involves the central FinOps team generating a dashboard or a monthly report and sending it to a specific engineering pod saying, hey, your specific microservice team consumed $50,000 in cloud resources this month.
Okay, so they know about it.
It creates awareness, but the central IT department still physically pays the invoice. Chargeback, on the other hand, is about ultimate accountability.
Chargeback has financial teeth.
Yes. In a chargeback model, those cloud costs are dynamically allocated and shifted directly to the profit and loss statement, the P&L, of that specific consuming business unit. Central IT no longer absorbs the cloud bill as a massive blended corporate overhead cost.
Okay, let's map out the political reality of that shift. If I am the vice president of engineering for a company's mobile application under a chargeback model, my team's cloud waste is deducted directly from my department's operational budget. It actively impacts my departmental bottom line.
Which fundamentally alters your management behavior. Suddenly you, as the VP, care deeply about whether your development clusters are running pointlessly over the weekend.
Because it's coming out of my pocket now.
Exactly. Every dollar wasted on idle compute is a dollar you cannot use to hire a new senior developer or buy better CI/CD tools or fund a team offsite. The Vera AI data definitively proves this behavioral shift.
What's the impact?
Organizations that successfully transition from central IT billing to a decentralized chargeback model see their overall waste rates drop by 9 to 14 percentage points.
Because it perfectly aligns the financial consequence with the provisioning power. When the engineer who clicks deploy is accountable to the manager who pays the bill, the friction resolves itself. But I have to imagine implementing chargeback in a legacy enterprise is a political bloodbath.
Oh, it is often the hardest cultural initiative a CTO will undertake. Department heads will fight viciously against it because for years they have been consuming unlimited, free infrastructure subsidized by central IT.
And now the free ride is over.
Suddenly exposing their true operating margins is highly confrontational, but once implemented, it creates a self-regulating financial feedback loop.
But even with a perfect feedback loop, even with flawless human behavior, 100% tagging compliance, and ironclad chargeback policies, we eventually hit a ceiling, don't we?
We do.
Because modern cloud architecture in 2026, specifically containerized microservices, is simply too hyper-complex, too ephemeral, to be optimized manually by humans. Which brings us to technical strategy 3, the deployment of automation, artificial intelligence, and dynamic right-sizing.
This is where we have to deeply analyze Kubernetes. Kubernetes has solidified its position as the de facto operating system of the cloud, acting as the connective orchestration tissue for almost all hybrid and multi-cloud environments.
But it has a dark side for costs, right?
It is notoriously hostile to manual cost optimization. Data from Cast.ai indicates that enterprise Kubernetes infrastructure is routinely over-provisioned by an average of 40%.
Help me understand the mechanics of that. Kubernetes is celebrated as this hyper-efficient container orchestrator that can pack workloads tightly. Why is it inherently so prone to over-provisioning?
It comes down to how the core Kubernetes scheduling algorithm, the kube scheduler, makes decisions. The scheduler is designed to optimize for system resilience, stability, and guaranteed availability. It is a fair system. When a developer submits a pod to be deployed, they define requests and limits. A request is the minimum amount of CPU and memory the pod needs to run.
And engineers, as we discussed earlier, inflate those requests to be safe.
Exactly. Now, the kube scheduler looks at these inflated requests and searches for a node, a virtual machine with enough capacity to host it. It does not natively look at your AWS billing invoice and say, let's bin pack these containers as tightly as physically possible onto the cheapest instances to save this company money.
That's not its job.
Instead, it spreads workloads out, ensuring they have plenty of unreserved headroom to handle sudden spikes.
So it's optimizing for survival, not unit economics.
Correct. And because the actual underlying cloud costs become obfuscated inside the abstraction layer of Kubernetes, engineering teams simply keep scaling up the underlying node pools. Manual right-sizing in this environment is mathematically impossible.
There are just too many moving parts.
You cannot employ a human to stare at a Grafana dashboard 24/7, trying to deduce which specific microservice pod requires 100 millicores less CPU at 3.0 a.m., and then manually rewriting the YAML manifests.
This sounds like moving from manually checking your home's water meter every month to having a smart valve system that detects a leak in the pipes and shuts off the water instantly. So how do we solve this mathematically in 2026? What are the specific automated software interventions that take the human out of the loop?
The optimization platforms we are seeing today rely on 3 major technical leaps. The first is highly granular, real-time anomaly detection driven by time series databases.
How is that different from what we used to do?
Well, historically, engineering teams discovered a runaway workload, a recursive Lambda function, or a massive egress mistake when the monthly invoice arrived 30 to 45 days later.
Oh man, I've been there. The end-of-month heart attack when the AWS bill is triple what you expected.
Right. But today, using advanced ML baselining, anomalies are flagged and often automatically throttled within hours. The financial telemetry data shows that identifying and mitigating a cost spike within a 24-hour window allows an enterprise to recover 60 to 70% of that anomalous spend.
Compared to waiting for the invoice.
If you wait for the monthly billing cycle, your maximum recovery is only 15 to 25% because the capital has already been burned.
That water meter analogy really holds up. The second major leap involves dynamic commitment strategies, right? This directly addresses the unused licenses and reservations we discussed in Category 3.
Yes, platforms like Usage.ai specialize in abstracting the procurement layer. Instead of a human finance team attempting to forecast what the company's compute footprint will look like in 11 to 36 months, and inevitably guessing wrong, these platforms use algorithmic trading concepts.
Wait, how does that actually work under the hood? Are they just buying and selling on a marketplace?
Essentially, yes. The algorithms continuously analyze the company's real-time compute usage patterns against the provider's secondary marketplace. They dynamically buy, sell, or shift commitment capacity on the back end multiple times a day.
That's incredible.
They ensure that the company is constantly receiving the maximum discounted rate without ever being financially locked into a 3-year commitment for a server architecture they might deprecate next month. It mathematically eliminates the risk of the commitment trap.
That is fascinating. It's essentially treating cloud procurement like high-frequency stock trading.
And what about Kubernetes specifically? How does a platform actually fix the kube scheduler's inefficiency?
That is the third leap. Autonomous Kubernetes workload optimization. Platforms like Cast.ai operate deep inside the cluster. They utilize machine learning to constantly analyze the delta between what a container requested in its configuration file and what it is actually utilizing in real time under live traffic.
And when it sees a discrepancy, let's say I requested 4 CPUs, but I'm only using one, the platform seamlessly patches the workload to right-size it, dynamically bin packing the container's PIDR, and simultaneously scaling the underlying cloud nodes down. It does this autonomously, without requiring a developer to approve a pull request. Furthermore, it actively leverages spot instances.
Let's clarify spot instances for the audience, because they carry a reputation for being dangerous.
They do. Spot instances are spare compute capacity that cloud providers auction off at massive discounts, often 70 to 90% off the standard price. The catch, and the reason they are considered dangerous, is that the provider can reclaim that server at any time, giving you a mere 2-minute warning before they terminate your machine.
Which is terrifying for a production workload. If your app is running on that machine, it just dies.
Exactly, which is why humans struggle to use them for critical workloads. But AI platforms can predict these interruptions using historical market data, and they can gracefully drain the workload and migrate it to a stable on-demand instance in milliseconds long before the 2-minute window expires.
And what's the financial impact of that?
Cast.ai's telemetry reports that this level of autonomous AI intervention, combining real-time right-sizing with automated spot instance utilization, cuts aggregate Kubernetes infrastructure bills by an average of 63%.
63%. When you apply that to a $5 million Kubernetes cluster, the capital recovery is transformational. But I want to inject some skepticism here. Handing the keys to your core production infrastructure over to a third-party AI algorithm that is constantly deleting and creating servers sounds like a recipe for latency spikes or catastrophic failure. Is the industry broadly trusting this yet?
Trust is building, primarily because the financial pressure is forcing the issue. But you are highlighting a crucial point made by Vera AI. You do not just purchase an AI tool, plug it in, and walk away.
It's not a magic bullet.
No, a mature organization treats this holistically. The ROI of a full FinOps program relies on layering these strategies. You need the basic runtime hygiene, you need the organizational chargeback culture to align incentives, and Dean, you need the AI automation to handle the hyper-complex microsecond decisions.
It is a complete evolution of how an engineering organization operates.
It is a massive undertaking. It typically requires 6 to 12 months to fully implement across a mature enterprise. But the data shows the financial reality. The net ROI exceeds 5-to-1 for organizations spending over $5 million annually.
That's a serious return.
For every single dollar you invest in FinOps personnel, cultural training, and AI tooling, you retrieve $5 in pure recovered waste. And perhaps more importantly than the capital, this automation returns an engineer's most valuable non-renewable asset, which is time. They are liberated from the drudgery of manually tuning YAML files to save $50.
Let's synthesize all of these distinct threads because this has been a remarkably dense journey. We began at the macro level, confronting a $1 trillion market, masking a $27.1 billion problem of pure idle waste.
Right, and we established that the root cause is not engineering malice, but a structural paradigm blind spot, applying the legacy always-on assumption of owned data centers to the variable running meter of the cloud.
We forensically dissected the waste into its core anatomy. The silent accumulation of zombies, the rampant over-provisioning driven by fear of outages, the irony of unused financial commitments, and the hidden architectural tax of egress. We found it thriving disproportionately in non-production workloads, accelerated by the velocity-first culture of tech companies and the broken procurement cycles of the public sector.
And finally, we mapped the escalating technical interventions, establishing basic hygiene through a zero-cost non-production runtime charter, enforcing organizational accountability by shifting from central billing to strict tagging and chargeback models, and ultimately deploying autonomous AI to mathematically right-size hypercomplex Kubernetes environments in real time.
So if you were an engineering manager, a platform architect, or a startup founder listening to this deep dive, why does this granular level of cloud optimization actually matter to you? The core takeaway is that cloud waste is not merely a spreadsheet problem for the finance department. It is a direct, insidious attack on engineering speed.
That is the ultimate consequence. Unowned, wasteful infrastructure spend eventually creates immense top-down budget pressure. When the bill gets too high, finance reacts by instituting heavy governance and approval friction for every new engineering project.
And that bureaucratic friction slows down the exact agility, the exact freedom to experiment that moving to the cloud was supposed to enable in the first place.
Exactly. You optimize the underlying cost, not just to save a few dollars, but so you can buy back your engineering speed and operational freedom. It really is that fundamental. It is the prerequisite for scaling efficiently.
Which leaves me with one final provocative thought for you to consider, based on the trajectory of the automated tooling we discussed. If platforms like Cast.ai and Usage.ai are getting this exceptionally good at instantly, autonomously right-sizing our infrastructure and programmatically trading financial commitments in real time, are we approaching an event horizon?
It's a fascinating question.
Are we moving toward a future where the human concept of buying cloud capacity disappears entirely, replaced by autonomous, interconnected AI systems that negotiate and trade raw compute power in milliseconds, operating exactly like algorithmic, high-frequency trading engines?
It is a profound logical conclusion. If the infrastructure meter runs autonomously and the workloads scale autonomously, the procurement layer inevitably must become autonomous as well.
Something to heavily mull over the next time you authorize a deployment or stare down your monthly AWS invoice. Thank you for joining us on this deep dive into the architecture of cloud efficiency. We will catch you on the next one.